In this video, let us derive Poynting's theorem. The equations which govern electromagnetic fields are called Maxwell's equations. Now let us write Maxwell's equation in differential form, which are given by del dot D equal to rho, del dot B equal to 0, del cross E equal to minus dou B by dou T, del cross H is equal to J plus dou D by dou T. Here D is the electric displacement vector, B is the magnetic field vector or magnetic field strength, E is the electric field vector, J is the current density here. These four equations are called four fundamental equations in electromagnetic theory, named as Maxwell's equations. To derive Poynting's theorem, take equation number 3 or the third equation of Maxwell's equation. Take scalar product of equation 3 with H vector. You will get H dot del cross E equal to minus H dou B dou T. Again, let us take a scalar product of equation 4 with the electric field vector E. We will get E dot del cross H vector equal to E dot J plus E into dou D by dou T. So, we have equation 5 and equation 6. Now, let us do equation 5 minus equation 6, that is subtracting equation 6 from equation 5. In the left hand side, you will have H dot del cross E minus E into del cross H, and on the right hand side, we will have minus H dou B by dou T minus E into dou D by dou T minus E dot J. And the next equation, let's pull a minus sign from the right hand side. If you pull it, we will have minus H dot dou B by dou T plus E into dou D by dou T minus E dot J. So this equation, let us name it as equation number 7. Using a vector identity, del dot E cross H, which is expanded as H dot del cross E minus E into, that is E dot del cross H. Using this vector identity, equation 7, the left hand side of the equation 7 reduces to del dot E cross H is equal to minus H dou B by dou T plus E in E dot dou D by dou T minus E dot J. If in case the medium is linear, then we can write B is equal to mu H and the displacement vector D is equal to epsilon E, where mu and epsilon are the permeability and permittivity of the medium. Now, from equation 9, the second term of the right hand side, we have E dot dou D by dou T, which is written as E into dou by dou T. In place of D, we are writing epsilon E, and we can pull this epsilon outside since it is a constant, and we are bringing that E inside. So to make this or to bring this E inside, we are multiplying by a half here. So this becomes 1 by 2 dou by dou T, that is to bring it inside the differential. We are multiplying it by 1 by 2. So it is 1 by 2 dou by dou T E, and then we are bringing the epsilon inside. So this epsilon E again gives you D. So we get dou by dou T of 1 by 2 E dot D. Again, in the same way, H dot dou B by dou T can be written as H into dou by dou T mu H. Then again, we are going to pull this H, push it inside the differential. So when you differentiate it, for example, if you differentiate H square, this the 1 by 2 from which is written front gets cancelled because of this. When you differentiate H square, you will get 2H. this h and h, I mean this 2 and 2 and will get cancelled. So finally you will get dou by dou t into 1 by 2 h dot b. So the equation 9 becomes del dot E cross H equal to minus dou by dou t. In place of H dot dou b by dou t, now we have 1 by 2 E dot d plus H dot b minus J dot E vector. Let us take it as equation number 13. To get the physical significance of equation 13, what really this equation 13 represents, we are going to integrate it over a volume which is bounded by over a volume V bounded by a surface S. So this is integrated over a V represents the triple integral here, del dot E cross H vector into dV is equal to minus integral over V, that is again it is a triple integral, dou by dou t into half E dot d plus H dot b into dV minus integral V J dot E into dV. On the left hand side, I am going to convert that triple integral into a double integral. For this I am making use of a Gauss divergence theorem. According to Gauss divergence theorem, integral of V del dot E cross H vector can be written as a closed integral over a surface S E cross H into ds. Now we are substituting this value in the left hand side of equation 14. We get the closed integral E cross H into ds is equal to minus d by dt into integral V 1 by 2 E dot d plus H dot b into dV minus integral V J dot E into dV. For our convenience, we are rearranging or we are bringing this minus J dot E dot dV into the left hand side and keeping everything on the other side. We get minus integral V J dot E into dV equal to d by dt into integral 1 by 2 E dot d plus H dot b into dV plus closed integral over S E cross H vector into ds. So this is the main equation, or it is called as an energy equation, and here we are going to interpret the each and every term of this equation to get a physical significance of what this energy equation represents. Now let us get a physical significance of the left hand side, that is integral over V J dot E into dV. For this we are choosing let us consider a charged particle of charge q which moves with a velocity v under the combined effect of mechanical, electrical and magnetic forces. So when a charged particle moving in an electromagnetic field, it experiences a force both due to both field vectors E and B vector, and we know the force F is equal to Q times E because of the electric field, and Lorentz force acting on the charged particle in a magnetic field F is given by Q times V into B. So combinedly we have wrote F is equal to keeping the Q outside, so it is E plus V cross B vector. We all know this magnetic force acts always perpendicular to the velocity, hence we can say this magnetic field does not do any work there. So for a single charge q, the rate of doing work by an electromagnetic field E and B vector is dou W by dou T. So W is the work, so the rate of doing work is dou W by dou T. It is given by F into V vector. We know in general the work is given by work into displacement. So rate of doing work, so force into displacement by the time taken, its velocity, so it is F into V. We have already F is equal to Q into E plus V into V cross B into V. We have already said that magnetic field does not do any, it doesn't do any work, so the magnetic field component, the force or the work due to the magnetic field component goes to 0. Finally we get Q into E vector into V. If we take Fm is representing the mechanical force or the work done by the mechanical force against the magnetic field vector per unit time, then the rate at which the mechanical work is done on the particle, charged particle, is dou Wn by dou t. Again we can write Fm vector into V, which is equivalent or equal to minus F into V. Here a negative sign is introduced because the mechanical force is done against the electromagnetic force. Since it is against the electromagnetic field, we have introduced a minus sign here, so it is minus Q E V. We have already value for F dot V, so it is minus Q E dot V. If the electromagnetic field consists of more than one charge or of group of charges which is moving at different velocities, for example, we say the electromagnetic field has Ni charges which carries a charge of Qi moving with the velocity Vi. Here I is for 1 to n particles, then dou W by m by dou t can be given as minus I integral I Ni Qi Vi into Ei. We are just simply multiplying Ni over this dou Wm by dou t. In this case, the current density J is equal to summed over I Ji vector. So this Ji vector is nothing but Ni Qi Vi. Ni Qi Vi. So we can write in place of summed over I Ni Qi Vi as Ji, or we can, in general we can write it as dou W by dou t is equal to minus J dot E vector. Actually this equation represents power density that gets transferred into the electromagnetic field. Hence we can say the integral minus integral E dot J dV represents the amount or the rate of energy that gets transferred into the electromagnetic field through the motion of charges over a volume V. If in case there is no charges or no sources of EMF in that volume, then this term minus E dot J dV is equal to minus J square by sigma dV, where E is, we know J is equal to sigma E. In place of E we are writing J by sigma, and this quantity is negative, and it represents the negative rate of heat energy that is produced in the electromagnetic field. Now moving to the right hand side of the energy equation. The first term of the energy equation is d by dt into integral of half E dot d plus h dot b into dv. Let us interpret that now. We have already derived equations. We already knew that integral of half E dot d into dv is equal to UE, which is nothing but electrostatic potential energy in volume V, and integral half h dot b into dv represents which is the magnetic energy in volume V. So we can write the U is equal to UE plus that is the sum of electrostatic potential energy and magnetic energy in volume V, which is equal to integral V half E dot d plus h dot b into dv, which represents some sort of a potential energy of the electromagnetic field. And let us not attribute this potential energy to the charged particle alone, but instead consider this term as a field energy, and this energy is called as electromagnetic field energy in volume V. So this term half E dot d plus h dot b can be represented by small u, which is the energy density of the electromagnetic field, and we can write this d by dt into integral of half E dot d plus h dot b into dv dv as the rate of electromagnetic energy which is stored in volume V. So this d by dt of integral half E dot d plus h dot b into dv tells you the rate of electromagnetic energy that has been stored in volume V. Now let us move to the second term of the right hand side. This closed integral over E cross H vector into ds can be interpreted as a surface integral term which includes both electric and magnetic fields, and which represents the rate of energy flow across a surface, or we can say it is equal to the amount of electromagnetic energy that is crossing the closed surface per second. And this vector E cross H vector can be represented by a symbol S, which is known as Poynting's vector. So the third term of the energy equation gives you the amount of energy flow per unit time per unit area. So far we have interpreted all the three terms of the energy equation. Now let us interpret the energy equation combinedly. The integral form energy equation is now turned into a differential form. That means we have minus J dot E equal to dou U by dou T. This energy density U is written here in place of half E dot D plus H dot B plus del dot S. Here we know S is equal to E cross H. So this is the energy equation. Bringing everything into the one side, we have J dot E plus dou U by dou T plus del dot S is equal to 0. The physical meaning of this energy equation is that the time rate of change of electromagnetic energy with a certain volume plus time rate of energy flowing out through the boundary surface is equal to the power transferred into the electromagnetic field. So this is the statement of Poynting's theorem, and this is also called as the law of conservation of energy in electromagnetism. So we can literally say the rate of change of electromagnetic energy with a certain volume plus time and the rate of energy flowing through a closed surface is equal to the power transferred into the electromagnetic field. So this is what the Poynting's theorem is stating.